community team. It's April week 1, and we have a couple of demos to show you this week. First, we have Devin showing off a Parquet file from our place. So let's see what he's got there.
Hey guys, can you see my screen?
Yep.
Great. So this is, I'm gonna do a quick mention of this. I've got a blog post that goes into how the Parquet place data set was created. Just posted today. You can go ahead and read through it. But the end thing is we've gone from a 12 gigabyte compressed or 22 gigabyte uncompressed CSV to a 1.5 gigabyte Parquet file. So that's really handy for data read speeds when you're doing repeated analysis and restarting and stuff like that. But anyways, if you don't know what our place is, you've got a little bit more research to do, but I've got links in the blog. So anyways, jumping into the data, this is what the data looks like. I've gone ahead and cleaned it up and normalized it a bit just so it's a little bit easier to work with integer columns instead of textual columns. But the data set is composed of a timestamp, anonymized user ID, the RGB for the pixel, and then the actual pixel placement. X2 and Y2 here are not used for user edits, but they are when administrators needed to define a rectangle for moderator edits. They have a rectangle that defines content that they moderated out. But anyways, I've developed a couple queries around here. One of the ones is just some general statistics. You can look at the number of users, the number of coordinates, the number of colors, and we can go ahead and come look over at this. So you can see the first pixel was placed here, and then the last one was placed at this timestamp. Looks like there's about 10 million users. Funnily enough, there are the canvas ultimately was 2,000 pixels by 2,000 pixels, and so you'd expect the output to have 4 million coordinates, but it turns out some pixels were never picked. And I'm going to do a query about that in a second. There were 32 colors to choose from. There were 160 million entries in this table, and there were 19 administrator edits to the file. So speaking about that 4 million, some missing pixels, that's what I'm going to call a lonely pixel. So I'm going to go over here. I've got some ad hoc stuff that I've written today. I'm hoping to make this a little bit better in the future, but basically it allows me to dump a table into a PNG file so I can look at it. But basically we can find all the lonely pixels to see, out of all the 4 million pixels, which ones weren't in this data set right here. And then we can do a view on it, so we can write it out to an image file. And then if we want to look at the results, we can jump over here and we can see, here we go, we've got some lonely pixels, and they're represented as white, and black pixels are the non-lonely pixels. So we could zoom in here, and we could maybe, if we're really knowledgeable in our place, we can say, oh yeah, that's that group, or that's group. But I think it's interesting that 160 million pixel places, there were some that were never touched. And then correspondingly, you might want to ask, well, what about the places where there's only a single edit? And those are what I'm going to call one and done pixels, very similar to this. We can do a couple filtering. We can see stuff that was only edited exactly once. We'll write it out to a file, and it looks something like this. So these are the one and done pixels. So this is kind of a very interesting data set to play with. I haven't really done any visualizations of any of the time components of this, but I think that's really interesting too. And I'm hoping that other people can take this Parquet data set, which I think is a lot easier to work with than the CSV file, and produce other interesting visualizations. So I think I forgot to mention, but this Parquet file is posted on the blog, and you should be able to download it yourself and load it up into Deephaven.
All right, super cool. Yeah, our place was a interesting thing that pops up on Reddit every few years. All right, next up we have Nate demoing a timetable stream at Barrage Performance. So Nate, take it away. All right,
All right.
Here's Nate.
So the first thing I'm going to show you is something called the timetable stream, which is like a timetable, but is just the number of events that happened over the last cycle. On this particular machine, I'm running with an update graph cycle time of 50 milliseconds. And so this, you'd expect this timetable to update about 5 rows for every update. You can see in the video that it's only ticking every second, and that's because the UI has a 1 second. It's setting the interval update time with Barrage to be 1 second. And this is kind of like can be a nice way to create like a clock for, different kinds of fun programs that you can write in Deephaven. Okay, so the second thing that I'm going to show you is basically I'm going to send a large table that ticks using my timetable stream that'll change many rows at once and send it over Barrage, and then we can look at what the performance is. So I added a new in-memory table that kind of keeps around a histogram of latencies for various stats. So we've got basically, well, actually, I'll show you. Oh, no, Matt has them all. So like, this is showing you the stats for this particular performance log. So propagation time is how much time it takes to basically send an event to each client. Snapshot time is how much time it took to snapshot the table from the parent. The update job is like the entire off-thread aspect of Barrage. Write time is for for each client, how much time did it take to actually send this to the socket. I have how many megabits were written. The amount of time, and queue time is the amount of time that it takes to write the data off of the update graph into the Barrage message processor. And the aggregate time is the amount of time that it takes to accumulate messages in case there are multiple of them within a particular time period, or within an interval of for that Barrage message producer. So I have 2 hosts here that I'm working with so that I can show you this using worker to worker. Let's see, so I actually, on the first table, I created a table and I'm for the performance log, and here I'm going to pull it in and merge it with the local one so we can look at the results on just this one table, or on just this one machine. And I'm going to create my big 200,000 row table that ticks every time the clock changes. And here I have the clock changing at 50 milliseconds, which is on par with my clock cycle. And so it's just changing the entire table. Since the timetable stream is now lazy and I'm using an update view, the only real costs that are happening are the ones when the Barrage message producer needs to write the data from the parent table into its temporary stash, and then from when it reading from the temporary stash to building the messages that it sends to clients. And I'm actually going to close the one that's being sent to the UI. And on the other machine, I'm going to subscribe to it. So this is the full thing. And I'm also going to close this one that goes to the UI because I just want to focus on the worker-to-worker costs. So here you can see some interesting things like this is 59 megabits for every message that gets sent. And I believe at this rate, let's do divided by 5. Actually, yeah, so this is right now. I also have this set to update the statistics every 5 seconds. I typically am going to have it. The default is going to be 60 seconds, but for demoing purposes, I thought this would be more visible. But this is basically saying it's sending about 1,000 megabits per second, which is saturating the line between these 2 machines, and that's why that's why the count isn't 100, which is what you would expect. But yeah, so that's my demo.
All right, very cool. All right. That's all we have for this week. So we'll see you next week with another demo. Bye.